Hello students, in this video we'll see an example of computing a Fourier series and using that Fourier series to evaluate an infinite series. So let's consider the function f of theta is just theta, so a linear function on the interval 0 less than theta less than 2 pi, and extend this to be a periodic function. Extend to be periodic. F of theta is f of theta plus 2 pi, okay? And then let's find the Fourier coefficients of this function. So let's find f hat of 0, so it's f hat of 0, that's going to be 1 over 2 pi, the integral from 0 to pi, 2 pi in this case. Typically we use like negative pi to pi, but in this case it's easier to use 0 to pi, so I can sort of break the symmetry of this function. Okay, so what I'm going to do now is I'm going to say this is just f of theta, so I'm going to have an f of theta, which is just theta, e to the minus I 0 times theta d theta. So what we're going to have over here is we're going to have what? We're going to have, that's just 1. So this is going to be 1 over 2 pi. And then we're going to have theta squared over 2 from 0 to 2 pi. So we're going to have a 1 over 2 pi. And the top one is going to be a 4 pi squared over 2. 4 pi squared over 2. So I just get a what? I just get a total of pi from this, because the 4 over 2 is a 2. The 2 cancels out, and one of the pi's cancel out. So f hat of 0 is equal to pi. Excellent. Let's find f hat of n. So if n is not equal to 0, what's the nth Fourier coefficient of this function? 1 over 2 pi, the integral from 0 to 2 pi of theta e to the minus I n theta d theta. Let's integrate this by parts, okay? That's a typical technique with these Fourier coefficients. That's going to be my u, that's going to be my dv. So this is going to be a 1 over 2 pi. Then I'm going to have a u times v, which is going to be a theta, e to the minus I n theta over minus I n from 0 to 2 pi. And then a minus the integral of v du, so that's going to be a plus 1 over I n, pull that out. Integral from 0 to 2 pi. From 0 to 2 pi. I have that 1 over 2 pi in front of everything. Of just what? Just e the negative I n theta d theta. Of course, by 2 pi periodicity, those integrals are gone by orthogonality. Those are automatically 0. And so I'm just left with what? I'm just left with these numbers over here, so let's carefully do them. When I plug in theta equals 0, there's nothing, so I just have to deal with the theta equals to 2 pi, right? So when theta is equal to 2 pi, I'm going to have a 2 pi. Of course, e to the negative I n 2 pi is just equal to 1, so I have a negative over I n. Okay, so those 2 pi's are going to cancel out. And so this is going to be a 1 over negative I n. Of course, negative I is the same as 1 over I, right? So this is just going to be an I over n. All right, excellent. And so now I can write down the Fourier series for this function. So this function f of theta, so f of theta, is therefore equal to the 0 mode over here. So the 0 mode is just going to be pi plus the sum over the modes that aren't equal to 0 and not equal to 0, I n over what? E to the I n theta. E to the I n theta. So this is our representation for f of theta, right? So this is what theta is equal to. So this is a formula for theta. So this is equal to theta for theta between 0 and 2 pi. Beautiful. So we get this entire collection of infinite series from this result over here. What I'm interested in doing now is I'm interested in applying Parseval's theorem. So let's recall what Parseval's theorem says. So Parseval's theorem says the following. It says 1 over 2 pi, the integral from negative pi to pi, or 0 to 2 pi, by the same principle, right? F of x squared dx. Of course, for these 2 pi periodic functions, this is exactly the same as this for 2 pi periodic functions. I can shift it by anything I like. And here, I'm using the 2 pi periodic property. These things over here are the sum of the square of the Fourier coefficients. This is the sum over n and z of f hat of n squared, okay? So those are the Fourier coefficients. And so now what can I say about these things? So now I get this result for free. So what can I conclude from this? I can conclude from this that, well, it's sum of the square of the Fourier coefficients. So the first thing we do is find the L2 number of this function. So what's the L2 number of this function? So if I look at the L2 number of theta, that's going to be an integral from 0 to 2 pi of just theta squared d theta. That's the L2 norm squared, right? This is going to be equal to what? This is going to be 1 over 2 pi, and this is going to be a theta cubed over 3 from 0 to 2 pi. And so that's going to be a what? That's going to be a 8. So we're going to have a pi over 6. We have an 8 pi cubed. So we have 8 pi cubed over here, right? And then over a total of 6 pi. Okay. So we can simplify this a little bit. So I can cancel a 2 and cancel out a pi. So that's going to be a 4 pi squared over 3. So 4 pi squared over 3 is the L2 number of this function. And now if I sum the square of the Fourier coefficients, what's going to happen over here? So sum of the square of the Fourier coefficients, this is going to be equal to what? This has to be equal to, this is also equal to the sum, n not equal to 0, 1 over n squared, and then plus pi squared, So if we rearrange this, if I subtract off pi squared over here, I can conclude from this that the sum over n not equal to 0 of 1 over n squared is 4/3 minus 1 is just 1/3. So this is going to be pi squared over 3. But now this is a symmetric function over here, so I can say that from 1 to infinity is just half of this, right? So we therefore conclude, yet again, that the sum from 1 to infinity of 1 over n squared is pi squared over 6. And this, as we know, is just zeta of 2. So we're able to compute the Riemann Zeta function by computing the L2 number of this function theta. In fact, if you compute the L2 number of the function theta to the power k, you'll be able to find a formula for zeta of k. Of course, it's going to involve a lot more careful calculation. You're going to find a recursion to do that, but it's actually a lot easier to do using the Taylor expansion for using the Fourier series, using the Taylor expansion for x cotangent of x, which we'll see in a further video. Thank you very much.